Okay, so section 14.2 deals more with reaction rates and concentration and something we call the rate law. And to start with, in section 14.2, we want to talk about two different ways that you can find the reaction rate if you have a given set of data. So if you have time and the concentration of your product data, and if it's low resolution data, in other words, if you just have a few data points, then you really have no choice but to calculate the average reaction rate over a given time interval. We actually did an example of that in our last lecture, where we said, well, how much has the concentration changed? How much has the time changed? And you put it into the equation that the rate is equal to 1 over nu B times delta concentration of B over delta T. If instead of low resolution data, if you've used something like a electrochemical probe or a spectrophotometer, and you have high resolution time data, then you can say that the rate is equal to 1 over nu B times the slope of a tangent line at any point along this graph. And really the slope is just delta B over delta T with you have an infinitesimally small time step. So these two different definitions are actually quite consistent with each other. One thing that I forgot to draw attention to in section 14.1 is that the reaction rate often will change over the course of a reaction. Your tangent line here, for example, has a much steeper slope than the tangent line right here. And so when you're choosing your interval or when you're choosing your point to take a tangent line at, you're going to have to be mindful of how far along the reaction you are. Usually it makes sense to choose the earliest time interval that you reasonably can, and to choose points early on in the time to get what we call an initial rate. Okay, so let's put this a little bit into practice. All right, so let's say we've got some data like this. At time 0 and time 5 seconds and time 10 seconds and time 15 seconds, you measure the concentration of B, the molar concentration of B to be 0, 0.0160 molar, 0.0295 molar, and 0.0503 molar. Now let's suppose this is a reaction that goes A to 2B. This is low resolution data, so we're going to have to look at intervals. And let's figure out what the reaction rate is at each interval. We'll use the same equation. The rate is going to equal 1 over 2 because of that stoichiometric coefficient of 2. The change in the concentration of B over the change in time. And it looks like all of the time intervals that we can look at here are going to be 5-second intervals. It makes sense to choose the most narrow interval that we can. And so let's figure out the rate for this interval. Well, that's going to be 0.0160 divided by, and that's a molar, divided by 10 seconds. So that's going to be 0.00160 molar per second. What about this interval? That'll be 0.0295 minus 0.0160 molar. So what's the change in concentration over that interval? We'll divide that by 10 seconds. Only this time I need to quickly sit down and run those numbers. Okay, so it'll be 0.0295 minus 0.016, and so that's going to be 0.00135 molar per second. And over this final interval, then it'll be 0.0503 molar minus 0.0295 molar, again divided by 10 seconds. Uh, 0.0503 minus 0.0295. That's going to be, hold up. Well, those are the numbers that I gave you. I'm pretty sure I've written them down wrong. I think that was supposed to be a 403. That makes more sense. So let me quickly fix that. That should be a 403 and a 403. Now it makes sense. 0.00108. molar per second. Okay, so we see the reaction slowing down a little bit over time, which is quite normal. Now we can express the reaction rate across all times with a simple equation called the rate law. The rate law is, let's look at an example of a reaction. Here I've given you a generic reaction, reactants A and B with stoichiometric coefficients of little a and little b are going to form products C and D with stoichiometric coefficients little c and little d. So for a reaction like this, the rate is going to equal K times the concentration of A raised to some power. I'll just leave it as the variable m. We don't know what power that is yet. Times B raised to some power, which we'll call the variable n. And it's really important to note that all reactants are included in the rate law, but products are not. And that these coefficients m and n, at least for now, they could be anything. They have no relation to, say, the stoichiometric coefficients, or the molar mass, or the concentration itself, or anything else. They're going to be some number, and our goal is to figure out their value. If we, they are going to be an integer, and so if m could be 0, and this would be what we call a reaction which is 0th order with respect to reactant A. M could be 1, and this is what we would call first order with respect to reactant A, and M could be 2. I bet you can guess what this will be called. Second order with respect to reactant A. And then we could also look at the value of N. A reaction could be 0th order, 1st order, or 2nd order with respect to reactant B. And if you had a more complex reaction, basically every reactant will have its own reaction order, which is a description of the value of this exponent in the rate law. Now we can add up M plus N, and this will be the overall reaction order. The overall reaction order. Okay, so let's look at some examples. Okay, for now, I'll just give you rate laws and ask you what the reaction order is, or give you reaction orders and ask you to give me the rate law. Okay, so if the rate is equal to K times the concentration of A squared times the concentration of B, then this reaction is going to be 2nd order with respect to A, 1st order with respect to B, and 3rd order overall. If I have something like this, then we have a reaction which is 0th order with respect to A. A raised to the 0th power is just 1, and so we just don't write it. And 1st order with respect to B, and 1st order overall. And then what if I have 1st order with respect to A, and 1st order with respect to B? How would that rate law look? Well, the rate would equal K times A raised to the 1st power times B raised to the 1st power. Okay, and all this time I've kind of been writing these K's. This is called the rate constant. Each reaction is going to have its own rate constant, and we'll see later on, in fact, that the rate constant depends on temperature, and this little K here is actually worth a whole day's worth of material analyzing the K itself. For now, it's just a constant, and we're really concerned about the reaction orders with respect to concentrations of different reactants. So if I have that definition of a rate law, I know that the rate is going to equal K A squared, for example, for a reaction which is 2nd order with respect to A. And I know that the rate is equal to 1 over nu A times the change in the concentration of A over the change in time. Well, I can set these two equal to each other. So K A squared is going to equal 1 over nu A delta A over delta T. Or what I should really do is make this a little bit more generic and say it's K A to the M, B to the N, and then this could be, doesn't have to be A, could be any chemical species that is participating in this reaction. It could be a product, it could be a reactant, it doesn't matter. Now, this right here is going to be useful to us for both this textbook section and section 14.3. This equation here is kind of the important, most essential equation to get at how we determine the reaction order using experimental data. And so the idea is, if I can calculate the rate under two different conditions, I'm sorry, I don't calculate the rate, I measure the rate. If I can observe the rate under two different conditions, then I can compare those two conditions and figure out what the reaction order is. What we'll want to do is carefully select two different conditions where maybe your concentration of B is the same in both cases and the concentration of A is changed by some regular amount, like maybe it's doubled. And so if you measure the reaction rate under conditions where A is doubled, then we can, well, why don't we do the derivation really quickly, and then I'll give you the bottom line of it. Okay, so if I have trial 1 and trial 2, trial 1, oh goodness. You know what I'm going to do? I'm actually going to use some example data from the textbook. That's going to be easiest. Okay, so here we see a reaction where we've done several trials. You only really need 3 of these trials, so trial 4 is superfluous, we can just ignore it. Under these conditions, with 0.025 molar in both A and B, we measured a reaction rate of 2.04 times 10 to the negative third molar per second. And in trial 2, you'll notice we kept the amount of B the same. And we've doubled the amount of A. So let's, oops, I moved the wrong thing. There we go. Let's see how that's going to help us. If I take the ratio of rate 2 over rate 1, I can set up this ratio. And what is rate 2 equal to? Rate 2 is equal to K times the concentration of A in the second trial, which is 0.0500 molar, raised to some unknown power m, times the concentration of B, 0.0250 molar, raised to some unknown concentration n. Remember, that's the rate is equal to this. That's just the definition of the rate law. And if I divide that by rate 1, well, what is rate 1? Over here it's going to be K times the concentration of A for trial 1 and the concentration of B for trial 1. So these are my conditions for trial 2, these are my conditions for trial 1. And let's put in actual numbers here, right? Rate 2, we've got numbers for that. Rate 2 was 8.16 times 10 to the negative third. And rate 1 was 2.04 times 10 to the negative third molar. And this looks incredibly intimidating, especially since you've got unknown variables in the exponents here. But if we look closely, we see that we can do a lot of cancellations. K cancels, and because these quantities are the same, everything about reactant B cancels. Now these are raised to that same power of m. And so what I can do is put 0.0500 over 0.0250. I can put them in together in a parenthesis with the m on the outside. And of course, 0.05 over 0.025, those were intentionally chosen to be a simple ratio of 2. 2 raised to the power of m is what we get on the right side. And then if we look on the left side, 8.16 times 10 to the negative third divided by 2.04 times 10 to the negative third. We can put that into our calculator, and what we'll find is that is 4.00. And so now it doesn't look too bad. 2 raised to some power is equal to 4. Now technically we can solve this regardless of whether m is an integer or not. We would have to use logarithms, right? So I could take the natural log of 4 is going to equal the natural log of 2 to the m. And there's this great property of natural logs where the m can come out in front. So I'll get the natural log of 4 is equal to m times the natural log of 2. And then I can rearrange this. Sorry about that. Okay. Then we can rearrange this so that m, our unknown exponent, is going to equal the natural log of 4 divided by the natural log of 2. Is that right? Have I done it all right? I believe so. And we'd be able to calculate the value of m that way. But I think all this time I've been talking about natural logs, you're probably screaming in your head that you know the value of m. 2 raised to what power equals 4? 2 squared equals 4. M, in this case, is equal to 2. 2 squared equals 4. That's easy, easy math. And as long as you choose easy ratios here, then you're likely to get easy ratios there, and you'll be able to do it in your head. If you double the concentration and your rate doubles, that's a first order. If you double your concentration and the rate quadruples, like we've done here, that's second order. If you double the concentration and the rate remains the same, that's 0th order. So let's go back to our data here. Basically what we found out is that our reaction is second order with respect to A. Now let's look at trials 2 and 3. If we compare trial 2 to trial 3, now the concentration of A is constant at 0.05, and the concentration of B has doubled. Well, looking at these numbers, 0.008 versus 0.016, it's pretty clear that the rate has also doubled. You can put those in your calculator to double check, but I doubled the concentration of B and my rate doubled. So that means that we are first order with respect to B. Or in other words, that N is equal to 1. And so we get rate is equal to K times the concentration of A squared and the concentration of B, based on this table of data. So again, use simple ratios, doubling concentrations, keep track of keeping one of them constant and doubling the other, and these are actually pretty easy, and you don't need to use your logarithms or even your calculator if you're okay at doing some simple math in your head. Now, after you have calculated your reaction rate law, you can actually pick any one of your data points and go back and calculate the value for K, your rate constant. And so let's go ahead and do that. We'll just pick the first data point. So our rate again is point, what is it? 0.00204, 0.00204 molar per second is going to equal K times 0.0250 molar squared times 0.0250 molar to the first power. And we can solve for K now. It's a bit tedious, but if you've got a calculator, then it's not that bad at all. So I'm going to say K is equal to 0.00204 divided by 0.0250, and that'll be raised to the third power, because we've got the 0.0250 squared and then the 0.0250 to the first power. We can just cube that. And so K is equal to, looks like 130.6. And let's be careful about our units. So there's an inverse second, right? Because we have the molar per second. But then we had 1 molar here, and we divided it by molar cubed. And so we'll have molar squared. 1 over molar squared second, or inverse molar squared inverse seconds. Now, those units may seem a little strange, but the value of the units for K are going to be just whatever they need to be to match everything else. If you change the reaction order, or if you have a reaction with a different reaction order, then the units for K are going to have to change as well. And I think that that is all neatly summarized in table 14.4. So if you have an overall reaction order of 0, then your rate law is just going to be the rate is equal to K, right? And your units of K will be molar per second. If your overall reaction order is 1, then your rate law is going to be something like rate is equal to K times A, or maybe it's K times B, but there's only one of them at any rate. And the units for your rate constant will be in inverse seconds. And then if you have a second order reaction overall, note that you can have that 2 different ways. You could have it second order with respect to one reactant, or first order with respect to each of 2 reactants. So 2 different types of rate laws, but in both cases, if it's second order overall, then your units will be inverse molar, inverse second. And then finally, if it's a third order reaction overall, just like we had A squared B, then you'll have inverse molar squared, inverse seconds for the units of K. All right, so this is just one way to find your rate law and your rate constant. This is called the initial rate method, because what you're doing is using an early interval to find out the rate under a number of different concentrations. You'll notice on our data table here, this was the initial rate. Because the rate changes over the course of the reaction, you'll want to make sure that you consistently measure that reaction rate in that first earliest interval that you can. Okay, and that is section 14.2.